Hello again, everyone, ladies and gents. Thanks for checking in again. This chapter, the topic of which stoichiometry, sure would lend itself to a lot of practice, and that's why I have seemingly a lot of videos for this chapter. All very exciting, I know, but in any case, the topic limiting reactants. The story is sometimes, for one reason or another, we don't have the right, we say stoichiometric quantities of 2 or 3 reactants mixing. Sometimes we have a little bit more of one than the other. Maybe we're being lazy, maybe we're being careless, maybe we're being dangerous, maybe we're being wasteful, but for some reason there's more of one than another. Or maybe we just don't care and we're interested in how much of a product we'll get, how much of a reaction we'll see. Yeah, and that's the topic, limiting reactants. Of course, I suppose. If we have a limiting reactant, that implies 2 or more reactants, usually just 2 to keep it simple. And we have a balanced equation that tells us how much of one relative to another in terms of moles. Then we go ahead and look at the mass amounts, the volume amounts, if it's a gas, it's a little more complicated. We'll do another video on gases. But today we'll just deal with grams and grams. Sometimes in a reaction, there may not be, maybe too much of one, not enough of another. The one that's too much is excess, the one that's not enough is limiting. And the limiting reactant always says or determines how far the reaction will go. If I had more of the limiting reactant, indeed the reaction would continue. Examples. Here's selenium hexachloride, burns in oxygen. Selenium dioxide, chlorine gas. I don't know about that. That sounds fishy, but anyways, let's go with it. You'll notice it's a balanced equation. There's one of these and one of these. That means it's a 1-to-1 mole ratio. So if I took a little bit less of this one and a little bit more of this one, I'd call this one excess, I'd call this one limiting. I guess that kind of makes sense. There's one of these and one of these, makes one of these and 3 of those. But in any case, this one, I got a little bit too much of that one, a little bit not enough of this one. You could say it that way, either way. I wish I had 2 moles of this, and I would get 2 moles of that, and it would react to give 6 moles of this. But I don't. So what do? I know, you do a calculation. Another example. What if I had 70 grams of selenium hexachloride, 50 grams of oxygen? There's no way to know this without converting grams to moles, because this weighs as a totally different mass than this, so I can't compare grams to grams. Almost never can you do that straight away. So I change grams to moles in both cases, add up the molar mass, selenium 6 chlorines, that's pretty heavy. It looks like I have a lot less of this one, 0.24, almost a quarter of a mole of this. I have more than 1.5 moles of this. So since it's a 1-to-1 ratio, I'd like one of these for one of these. If this is 1.56, I sure would like 1.56 moles of this, but I don't nearly have it, so I go with the 0.24 moles of selenium hexachloride, and I'll call that limiting. So if that is really limiting, then what I'll do is I'll say, go with the limiting amount, look at the mole ratio, put moles of selenium hexachloride on the bottom, 3 moles of chlorine gas on the top from the balanced equation. In a way, we've just skipped the first step of the 3-step gram to gram conversion that you might have watched in the basic stoichiometry video. Yeah, we've done that right here. So eliminated or done this earlier. Now we do the mole to mole ratio, and lastly convert moles of chlorine to grams of chlorine. 2 chlorines, 35.54 grams a piece or something like that. And lo and behold, I see the cancellation. And lo and behold, I know now how much chlorine gas I will get, 51 grams from this reaction. Gee, if I had a little bit more of this, then I would, a little bit more? No, I'm sorry, quite a bit more. Yeah. If I had 1.56 moles of this, I would like 1.56 moles of this to get 3 times that amount of moles of chlorine gas. All right, another example. Oh yeah, potassium hydroxide reacts with phosphoric acid. Balanced equation, 3-to-1 ratio. Interesting. So the simplest case scenario is just to say, well, I'll take 3 times more of this and this. And indeed, if you have moles, that works. 3 moles of this for every 1 mole of this. So if I had 2 moles of this, jack that up to 6 moles. But what if I didn't do it that way? What if oops, you didn't see that, did you? Yeah. What if I had 1 mole of this to every 1 mole of this? In other words, 4 moles of this and 4 moles of this. Well, focus on the balanced equation. It seems to say I need 3 moles of this for every 1 mole of this. So 3 times more of this than this. Well, if I have 4 moles of phosphoric acid, this stuff, Wouldn't I really rather have 12 moles of this? Because 3 times 4 is 12? Indeed. So again, this is limiting. If the balanced equation says I need more of something, I need indeed more moles, an increased number of moles, as compared to another reactant. Or take millimoles. Milli is just a 1/1000th of a mole. Convenient sometimes, many times for doing titrations. What if I had 37 millimoles of this and 100 millimoles of this? Well, one of these for every 3 of those, 3 of these for every 1 of those. So is 100 3 times larger than 37? And the answer is no, it's not. In other words, if I looked at the mole ratio, 3 to 1, I could take 37 millimoles of this, convert 1 millimole of phosphoric acid relating to 3 moles of KOH, and that would kind of imply to me that I would really like to have 111 millimoles of KOH, and I don't quite have that much. 111, I have only 100. So because of that, this is limiting. This is a little bit tricky until you get the hang of it. Here I made up some other random numbers. 0.817 moles of KOH, 0.295 moles of phosphoric acid. Now I could do this either way. I could start with this and convert it to an amount of this, or I could start with this and convert it to an amount of this. Looks like I started with the 0.817 and converted it to an amount of phosphoric acid. For 0.817 moles of KOH, I need 0.272 moles of phosphoric acid. Do I have 0.272 moles of phosphoric acid? Yes, I do, and it's a little bit more than that. So we do have 0.272 moles of phosphoric and more, so the phosphoric is excess and the 0.817 is limiting. Interesting. Or the other way to say it, no. I'm sorry, my bad. Let's continue with that then. Since this is limiting, then I'll take it and do the mole-to-mole comparison. Maybe I'm curious how much water I'll get. Oh yeah, there's the question mark. But 3 moles of KOH give 3 moles of water. It's a 3-to-3 ratio, which is also 1-to-1, but I always like to write the mole-to-mole ratio to remind myself of what I'm converting from and what I'm converting to. Then you change moles of water to grams of water. Oh goodness, if this isn't a lot to swallow in one sitting, I'll be surprised, but maybe it makes sense to you right away. 40 grams of this, 50 grams of this. I just made that up. I'm being silly because if I have a 4 here and a 5 here, an ignorant chemist, not a very good chemist, an ignorant student might say, well, why don't I just take 4 grams of this, or 5 grams of this, or 40 grams of this, and 50 grams of this? Well, yeah, that sounds good, but you can't compare grams to grams because this grammage, this molar mass, weighs different than this one. They weigh differently. So indeed, convert grams to moles, and 17 grams per mole for this, and 32 grams per mole for this, and it looks like I have a 4-to-5 ratio, so 5 is bigger than 4, so I would like a little bit more O2 than I have of NH3. Do I have more moles of O2 than I have of NH3? No, the 1.56 is smaller than the 2.35, so this one's limiting. I wish I had more of it. I wish I had actually a 5-to-4 ratio. I wish I had 5/4 more of this. What's 5/4 times this? Give me that much of oxygen. That's what I wish I had. Or rather, the reaction would go more completely if I did have that. So, yep. All right. Well, think about it, and we'll have to practice with it. So if I do indeed assume that and think that's true, and for the time being, I'm saying it's true, take the limiting reactant, change moles of your limiting reactant into moles of what you're curious about, perhaps moles of water, change moles of water to grams of water. Let's do one more. What if I started off similarly? Similarly, what if I had 40 grams of this and 100 grams of this? Just double it and see what happens. All right. 2.35 moles of ammonia, 3.12-ish moles of oxygen. Okay, 5-to-4. That's difficult because I do have more of oxygen now than I do of ammonia, but is it the right amount to use? Let me see. 3.12-ish moles of O2, do a mole ratio, converting moles of O2 to moles of NH3, and it looks like 2.5. So 2.5 moles of NH3 would be needed for 3.125 moles of oxygen. Do I have 2.50 moles of NH3? And it seems like I don't. So I think the NH3 is limiting in this case. This is smaller, and it's too small. Yes, I need a smaller quantity of it, but I did this little conversion right here to say but I wish I had 2.5 moles of NH3, a little bit more than 2.35. So if the NH3 is limiting, we can go with that, figure whatever other quantity we might like. If this were true, that 2.35 moles of ammonia would predict this, and it would also predict this, although I didn't bother to go through that calculation. One more, iron and sulfuric acid. 110 grams of iron, 280 grams of sulfuric acid. I have no idea how much hydrogen gas I'm going to get. So let's convert grams to moles. And hydrogen weighs 55.85, sulfuric acid 98-ish. And it looks like I'm going to get 1.97 moles of iron and 2.85 moles of sulfuric acid. And indeed, I need 3 moles of this to every 2 moles of this. This number is bigger than this number, so better check carefully. You can go with the iron, you can go with the sulfuric acid, doesn't matter. If the 2.85, I just flip this upside down. But with the iron, 1.97 moles of iron, 2 moles of iron, react with 3 moles of sulfuric acid, and 1.97 times 3 divided by 2, 2.955 moles of sulfuric acid. Do I have 2.955 moles of sulfuric acid? No, I don't. So with this much iron, I wish I had this much sulfuric acid. I don't. Therefore, the sulfuric acid is limiting. And if that's true, then I'll take that number, 2.85 moles of sulfuric acid, and I can work with it and ask the hydrogen question, convert moles of sulfuric acid to moles of hydrogen. Again, it happens to be a 3-to-3 ratio, but that's kind of a coincidence, so I should always write that down. Right, what I'm converting from, what I'm converting to. This comes from the balanced equation. Convert moles of hydrogen to grams of hydrogen. Hydrogen weighs like 1.008 or something like that. Whew, that's a mouthful. All right, guys, thanks for watching, and seriously, I admire your hard work. See you in class. Don't let up in your studies.